It's going to space charge, the mass is going to shift, and you're going to get a lower sensitivity because you're not going to get your full number of ions in. The key to not having to have lock masses in the system is it's all based on ATC. Linear trap is the same as your standalone linear trap. You must use this calibration solution to calibrate it. Caffeine and morphine ultramar. Can't get away from that. No FT.
So on this solution, how do I store it long term?
I just store it in refrigerate it. No, the bottom of it. If you store it in the refrigerator, normally what first happens is the caffeine will start to drop. You'll just spike more in from the stock. The one you worry about is the MRFA, this 4-peptide peak. When it starts to degrade, it methylates, and you'll start seeing 540. If 540 gets bigger than 524, it's going to pick the wrong peak, and the calibration is going to go to hell. So usually when you start seeing the 540 peak come up, it's time to throw it out and start moving. It's not going to be a problem in the FT. The FT only uses a window of 100 ppm. But the FT, you can use anything that you know the mass of. Don't have to use this. On your desktop, there's a shortcut, the FT mass editor. FT mass editor.
Cool?
Yep.
Okay. Now, remembering that in the back of the trap there was a hole, and that's where we're going to drop the FT ions. Okay? Okay, so to collect a spectrum on the ICR, first we're going to do the regular steps of the ion trap. So we're going to fill the ion trap, and we're going to do a quick dump to get the pre-scan amount for 1 millisecond. Then we're going to refill the ion trap, do our trapping of ions, cool them, dump them. So the first step is the injection. So that's the dumping out the back end of the ion trap into the ICR. We capture the ions, we excite them, we detect them, we get rid of them by quenching, and then we process the data. Okay. So here's a picture. Okay. So we have the ion trap. Okay. After the ion trap, the neat thing is every ion trap in the world is field upgradable. It's ready to have an FT on the back end. Okay. So all we do is we take a plate off the back. Okay, and we bolt on the ICR setup. It comes in a nice tube. It's all ready to go. Inside it has a short multipole, a medium length multipole, and a really long multipole. Okay, and then a 3-segment trap. Now, the pictures we show is not what you actually get. We actually do somewhere between a true 3-section trap, which is the normal academic trap, and the Brooker has the infinity cell for quantitative work. Ours is somewhat halfway in between. It's not enough infinity cell to infringe on patents, yet it's good enough to get decent quantitation off of.
So it's spacious enough to avoid charge.
Right, and what the key is, it's these end caps have resistive wiring. So when you look at this thing on the picture, you think, well, there should be about 12 wires going to it. There's actually about 50 wires going to it for the resistive coupling to make it more infinity-like. Okay? This sits inside a 7 Tesla actively shielded magnet, which you got to obviously fill with cryogenics to keep it cold. Okay? If you guys have any questions on magnet technology or supercon, let me know. Okay, if it's not intuitively obvious. And no, it is not plugged into the wall. Okay? So, what we do is we fill it, and then we dump, and we transmit. Okay, now, that sounds like a very simple process. It's actually rather complicated. But the problem is, we actually create a time of flight mass spectrometer inadvertently. So the ions leave the ICR cell as a nice tight packet. And as they fly, they actually separate spatially, with the lighter ions moving further along than the heavy ions. And when they come to the ICR, we have to recapture them. We can't capture the whole packet with equal efficiency. We can either efficiently capture the front end, the back end, or the center. So we're going to create a bias based upon shape. Does it make sense? Okay.
So why don't they just add something in the middle that sort of recongeals it? Sort of,
On the Orbi-trip, we developed the C-trip. Okay.
to minimize.
And that resaves them and injects them in properly. Okay. We don't know how to do that with the FT because you can't put anything really electronic inside the magnet. So I think this is one of our limitations we're always going to have with the FT, is this change in shape. Okay, now, there are several things you have to calibrate. The first one is you have to calibrate these voltages on all these transmission optics. Those voltages are mass dependent. So first and foremost is the voltages, the actual offsets and the RF intensity on those transmission optics creates a mass bias. The second mass bias you have to overcome, okay, is the flight time. So the question is when we open here, at the same time we open here, the question is when do we close? That's called the flight time. Okay? The flight time determines whether you capture the beginning, the middle, or the end with the highest efficiency. The third thing is the voltages on these trapping sections actually do change the mass bias. Make sense? That's part of what's called your transmission calibration. So now we're going to have, instead of one calibration, we're going to have 4 calibrations. We're going to have one calibration for the ICR cell, for the linear trap and its detectors. We're going to have a second calibration for transmission of those ions. Okay? That second calibration has 6 parts to it. Okay? It's got a positive ion for 195 to 2000 m/z scanning. Okay? It's got a positive part for, I think it's 98 to 980 scanning. And it's got a third calibration for 50 to about 850 scanning. So there's 3 different calibrations because each calibration is set up for different mass biasing, and that's dependent upon what your first mass is. Now, this seems like, why are you telling me this? Because it's very important if you ever do MSMS on the back end. You can do MSMS and detect on the back end. Okay? Well, if your full MS is scanning from 400 to 2000, and you break something apart at, say, 600 m/z, then you might be scanning from 200 to 1200. That puts you on a different calibration, which can give you a very different look. Okay? So make sure if you ever get into doing MSMS on the back end, which you might want to eventually do with ETD or something, or some of these other techniques that become available, or the pulse Q, you might want to look at what the calibrations are. Make sense? Okay, now, so here's a picture. So here's the ions in the linear, and they're going to come down through the transmission optics. Okay, this FT operates in a very similar fashion than the LTQ. We've got a trap in 3 dimensions. Okay, and just like the LTQ, we use the front section in the end section to provide Z trapping. So we drop the first section down. Down come the ions as a packet. When they enter, we raise the first section up and we trap them. And they go harmonically back and forth. Just like the linear. Exact same idea, exact same electronics, everything. It's just harmonic motion in the Z dimension. Any questions? No, cool. Okay, now, the next question is how do we handle ions in the XY dimension? Okay, now, our linear trap was 4 hyperbolic rods. Now what we have is 4 quarter circle pieces of copper plate. So we take very thin copper plate and we bend them to be a half circle, quarter circle, quarter circle. 4 quarter circles, not halves. Okay? One set of rods are called excites, and one set of rods are called detects. So we have detect plates and we have excite plates.